And my name is Sudha Isekimuto. I'm a researcher at InnoRenew CoE, and this webinar is conducted by PACK-NIN project. This project is funded by Marie Sklodowska-Curie Action, and the aim of this project is to use underutilized bio-based materials for value-added application. And part of this project today, our speaker is Associate Professor Dr. Matthew, and he's Associate Professor at the University of Primorska and a researcher at InnoRenew CoE. And he obtained a doctoral degree in 2014 in the field of food science and material science, mainly focusing on mechanical load transfer in composite materials. And then he has been involved with numerous international projects in variety of fields in InnoRenew, and mainly on valorization of underutilized materials. And he is also responsible for the Sustainable Built Environments MSc program at the University of Primorska, and he also guiding some PhD programs to PhD students. In this course, this MSc program course, he mainly focusing on wood anatomy, mechanical testing, non-destructive evaluation, and composite materials. Today, Dr. Matthew going to share the knowledge about improved performance of wood utilizing impregnated resins. So this webinar is recorded, and during the presentation, if you have any questions, please type in the chat session. So at the end of this presentation, we will address the questions. And now, Dr. Matthew, this floor is yours. Thank you for joining with us. Thank you. You can start.
Thanks,
please.
Thanks, Sudha. Good afternoon, everyone. Thank you for inviting me. Today, I wanted to introduce a little bit about densified wood projects that we've been working on. Not only the densification, but methods to stabilize these products after applying this densification treatment. So let me open up my presentation, share. Like this should be good. Okay. So I will talk about myself because everyone loves talking about themselves, but it will give you a little background into where I'm coming from and how I got to this point with densified wood. So I grew up in rural America in Iowa. So this is like cornfields and soybeans and cattle and pigs. So it was unique that I went to a forestry program because it was all agriculture. But for me, I was interested in doing something industrially, like industrial agriculture, which forestry kind of is as well, if you're doing it for logging. So this was the connection that I made. But after doing my bachelor's, I was able to travel to the state of Oregon, and there they have really strong wood science programs, which makes a little more sense because they're all covered by forests. And here I did my master's degree in work related to soy-based adhesives. So this is a soy protein adhesive that they're using in hardwood veneer panels. And I was trying to use this same formulation or recipe to use for OSB. And then after this, I worked in the industry for about a year, and then went back to Oregon State and started my PhD, where I looked at load transfer in composites. So this was like related to plywood and bond lines, but also to filler and reinforcements embedded in polymer matrices. So this was about 10 years at Oregon. And then after this time, I moved to Slovenia, which is very similar to Oregon in the fact that it's covered by forests. It has mountains near the seaside. And here I was able to start the master's study program at the University of Primorska, the Sustainable Built Environments. This is related to a lot of the work that I'm now doing, and Suda and everyone else from InnoRenew. And so it really pairs nicely with the courses that we teach and then the research that we're doing here. So in this program, as Suda mentioned, I'm teaching some basic wood science topics. Yeah. So yeah, also a researcher at InnoRenew. So I started in Slovenia teaching and doing this program only, and then we were successful with funding for the InnoRenew project. So that's the rest is history. Okay, so a little bit about my research topics. Yeah, I started with wood composites more. And then after meeting Andrea Kutnar, who specializes in thermo-hydromechanical treatments of wood, I started doing wood modification with her as well. And then after moving here, we got involved with the agricultural, the Mediterranean agricultural department at University of Primorska, where this is how I got a connection to olives. So I did a lot of work with trying to utilize olive waste streams and byproducts. And so this was a really interesting project I had for the last 4 years, and it got me interested in trying to use byproduct streams, agri-food side streams, and trying to use it in value-added materials. So this also is related to biorefining. But my true love is in microscopy, although this isn't, this unfortunately is not a lot of my time, but yeah, this is what I like to do if I have some free time. So the first, I'm going to talk about 2 different projects, both from a synthetic or non-bio-based approach, and then I want to talk about some work that is looking at bio-based impregnants in wood. So first, I wanted to talk about this project that we had with using poplar wood. This is a project that was born from an industrial collaboration with the company Metadynia. So Metadynia is a adhesives company for wood-based panels, specifically phenol formaldehyde-based resins, and they created in their labs a resin that could be transported long distances, which was stable over a long time. So their parents' company is in Russia, and they wanted to transport these resins across Siberia. So long times in not ideal environments, so they wanted it to be stable for a long time. Unfortunately, this didn't pan out for them, and they never used this recipe until they talked to us. The recipe was a very low molecular weight resin, which we identified as a possible resin for fixing and reducing set recovery in modified wood. So I will talk about this project now. So wood modification can be a lot of things. It can be chemical, thermal, mechanical. It can also go back to silvicultural practices. So in this Slovenian and Croatian Istrian region, there historically were a lot of oak forests. And the story goes that these oak trees were built the Venetian Navy, and that these oak trees are also what holds up Venice today. So there were a lot of forestry going on with these trees, including silviculture and shaping of the trees for different components of the Venetian Navy of the boats. So this isn't the modification that we're talking about today, but what we are doing is simply known as densified wood. So the reason you want to densify wood is that you can alter, maybe not improve, but alter mechanical properties of the original wood species to increase the number of applications, to target specific applications, and perhaps increase the value of low value species. So in our case, we were looking at using poplar because it's regionally available. It was first heavily planted for fiber, but then the fiber plants went away, so they have large plantations of poplar trees nearby in northern Italy, going up to Austria. And these are relatively low value wood species. So the densification, you can target different compression ratios, as you can see in the photo on the right. Yeah, there's a lot of things you can do here. So one more thing. The densified wood is not a new topic or a new technology. So this has been done in the past. There's been patents since before the First War, and the target here was during war times. There were shortages of metal in particular, and so they were trying to find to use wood to replace these components in airplanes and tanks, and so they were looking at impregnated beech veneers, and this patent is still around today. But for us, we have less military applications, but more for trade and perhaps logistics. So the densification process happens at the microscopic level. So if we look at, we'll say some tracheids, we represent them as these little open squares. And this is the process simplified a lot. So on the left side, you see the natural wood cell. So this is like a representative tracheid. And then moving on, you want to plasticize the wood cell material. And you can do this through chemical means, which the impregnants we use do. So they help soften and let these wood components slip. And we're also heating the wood cells at this time. So this helps the wood cells compress without cracking. So if you're cracking the cell wall, you're losing the strength and the original structure of the wood, and you're just smashing it. So there's a fine line between smashed wood and densified wood. So during this densification, you apply pressure to the desired thickness that you're targeting. And during this time, the ideal method is to cool while under pressure as well. So this cooling helps lock in this compression. If you don't do this, there is spring back in most panel products. So this even happens in plywood and OSB. And this is like a natural response to this pressure that you're inducing in the material. But the real challenge comes when you're adding moisture back into the wood, or if you expose it to moisture. So these are some images of a poplar, and this is actually poplar from South America. So it looks a little different than what we have here. But you can see that on the right side, the material is very dense, and the lumens and of the vessel elements are completely collapsed. So this is what's this is what is going on in the poplar wood. However, this image series is not before after, but it was actually the other way around. So we first imaged in the SEM the densified wood, and then we added water to the surface. And on the right side, that's what the same piece looked like after recovering from this densification. So this is a huge problem because you lose everything you're trying to accomplish if you are exposing it to wood. So this is the challenge of using densified wood, is how do you avoid this set recovery phenomena afterwards? So in the picture on the top, these are samples that we put in accelerated weathering machine. And on the right side, you can see some of the wood has recovered its original original dimensions. So the approach that we're using is to reduce set recovery by adding low molecular weight resins. So low molecular weight is something less than like 400. So these go into the cell lumens and also the cell walls. So once they're in there, you're compressing, and upon densification and pressing under temperature, these resins are then going to polymerize and set into a polymeric network. So these are the samples that we produced. We are using poplar, densified poplar, and then densified poplar with resin. So the purpose of this small study was to look at the effect of drying time before densification. So what you want to do is dry the impregnated wood before you densify to remove water. So these are the different times we used to dry out. The preparation of these samples is basically impregnation under vacuum in a vacuum chamber for a half hour. Then we are drying at 60 degrees, one of these whatever targeted drying time we're looking at. And then the pressing itself is in a hot press like the one on the right. This is a small press we have at the moment. We are upgrading this summer to a much larger one. But essentially the platen temperatures are around 170 degrees. And then you are holding this under temperature and pressure. And then you are again raising the temperature to over 200 degrees. So this is trying to make a sort of heat treatment of the wood, which is also good for reducing interactions with water. So after heating up and holding at these higher temperatures over 200 degrees, you're then lowering the temperature back down to 60. So this is what is going to really fix this densification in place. So to measure set recovery, we exposed samples to submersion. So we submerged them for a day, and then we dried them also for a day and measured the thickness after each cycle. So we did three of these cycles. So the results look something like this. So if we look at facet 1 on the left, this is cycle number 1. So the 72 is 72 hours drying, then up to 96 hours drying, and control is looking at densified wood without any impregnant in it. So this is just if you densify, put a piece of wood in there and densify. And so each one of these, what we're seeing is that 96 hours of drying does something different, right? So what's happening here is that the set recovery is almost 30%, the median is, and this is over dried. So you want some level of moisture still in the wood. Not only is it over dried, but it can also pre-cure the resin, which causes problems. So phenol resins are curing at higher temperatures, but they just cure faster at higher temperatures. So there can still be some reaction going on at lower temperatures. And so it's kind of we think it's a combination of these things. So this is good to know because drying takes a lot of time and money. So it's good that the better results are shorter drying times. We also looked at the mass loss when exposed to fungi. So in this study, we exposed it to white rot fungi and exposed it for, so every 2 weeks, we measured the mass loss up to a 10-week total exposure time. And the results look like this. The black is the reference. So this is the densified with no impregnant in it. And so we have quite high mass loss, which is what we would expect to see. So once you add any amount of, once you add these impregnants, you can see that there is much, much lower mass loss, something between 10 and 15% after 10 weeks. And what we see is that there's no real effect. Drying has no real effect on this these results, and that's to be expected. And the reason why we can expect that is because these impregnants are altering the nature of the wood cell wall itself, so they're chemically changing and making it unattractive for fungal growth and degradation. So concluding this study, we found that there was the drying time, changing the drying time had very little effect on the mass loss, but it did have a large effect on the set recovery because you're over drying if you leave it for too long. And yeah, the mass loss is affected by chemical changes in the cell wall when you introduce this impregnant. The other side of this story is that these phenols are coming from fossil fuels, so they are derived from non-renewable resources, and so everyone is trying to find imported and also renewable feedstock for all of their products. So after this study, I wanted to explore if there were bio-based options for these impregnants. And so this is when this next project came into play. I met Dr. Tamiz, who is in the audience, at a cost action. And we started talking about this. His research group was doing or is doing work with vegetable oils in modified and densified wood products. So we wrote a bilateral project between Slovenia and Turkey, and we're successful. And so I've been able to meet his student Antone and their research group, and find out a lot more about the use of vegetable oils in densified wood products, more specifically soybean oils. So this study is done to look at the performance of a bio-based impregnant. So I am truncating the study a lot. There were a lot of different tests and a lot of different permutations of adhesives and resins explored, but I am focusing on this epoxidized soy oil. So we again looked at dimensional stability and decay of these samples. The bio-based impregnants used are vegetable oil based. So these are a lot of things like soy, linseed, olive oil, canola. So this is coming from rapeseed. And the idea is that you utilize these unoccupied double bonds in the triglycerides. And so some oils are easier to work with than others. So linseed, for example, is already used in the wood industry. So on the top image on the right, they're applying a linseed oil, and this is a nice surface treatment, and it is a drying oil, what they call them. So if you leave this, it will polymerize on its own. However, if you leave olive oil out, it will not dry. So some oils like olive oil are more difficult to work with and to utilize for these impregnants. Yeah, I forget why I put cellobios here. I just wanted to mention that, yeah, we want these oils to interact with the hydroxyl groups in the cellobios in the wood. So the oil treatment itself, there are different methods you can use when you're impregnating wood. So you can have a full cell treatment. So this is basically filling everything. You're totally filling the wood with whatever impregnant you use. On the right is a study I did, and we used a full cell treatment with, it was modified olive oils actually. So these have really, really high retention rates. So if you can imagine, poplar is 300 kilos per cubic meter, and then you add 400 more, it really is adding an unacceptable amount of weight. The other problem is that these oils leach out of the wood, especially non-drying ones like olive oil. So what the treatment they used in this study was a empty cell. So this isn't relying on total bulking of the cells, but it's relying on the active decay resistance rather than just filling everything with oil to block any growth of fungi. So let's see. So here I was saying water, yeah. So for PF resins, like the previous study, these were using water. So water as a solvent, so you can dry this out. But these oil systems are not this way. So you are not drying oil out necessarily. So it's a little different treatment method. So for this ESO, so this is the epoxidized soybean oil, they had retention levels much lower than those of full cell treatments. So this is much more realistic values for retention, targeted retention levels. So once the material is introduced into the cells, it can be cured with some other chemical interaction in the wood and then densified in a similar way to what we used in the previous study. So the densification treatment was a little different than what we had, but they were targeting a 25 and 40% densification ratio. So they were steaming the material first. So this is to achieve this plasticization of the wood material before you're compressing it. They're compressing at essentially the same temperature as we were. And another difference here was the cooling, from what I understand, was done outside the press. So the results of this treatment, yeah. So we have the non-densified material, which is 300 kilos per cubic meter, and then you are increasing this value a lot. For set recovery, I've highlighted the ones I want to talk about. Let me move this window. Okay, so on the right side is untreated densified wood. So you can see that there is a lot of set recovery, which is expected because you're not trying to combat this set recovery at all, and you have this large amount of swelling. In the middle, you have the 40. You have epoxidized soybean oil at different levels of densification, and you are still seeing higher levels of set recovery than before. The treatments that did work in this study were with these epoxies, which are realistic for industrial products. So this less than 10% is really fixing the treatment in place. So if we do a comparison between the previous study and this one, we were seeing very low set recovery rates with the PF resin compared to these epoxidized soy oils. And so what we think is going on here is that there is pre-curing of the resin happening. Also, there is these cooling steps could be added to improve this set recovery values. And then, yeah, we want to avoid increasing drying time to limit the damage to cells. So there's some things to improve, but I think, yeah, some more work in this area. This topic will be very interesting because this is an important topic to keep after. So for the decay, these were exposed for 8 weeks, and the results look something like this. So yeah, so if you just look at the weeks 1 through 8 going to the right, and you compare these to the black line is from the previous study. They are, yeah, they're doing also doing well, and so you see that the reference wood values are, yeah, they vary quite a lot, but the epoxidized soy oil treated samples did well against the decay, the mass loss, both for brown rot and white rot, as we see here. Yeah, so just comparing, the mass loss was similar for both of these. So any variation that we see is, there's a lot of differences between these two studies, but it's good to see that we can agree on that these the decay resistance is related to these chemical changes in the wood cell wall, either by a bio-based impregnant or a synthetic one. So quickly wrapping up about this, these two studies, this PF resin at the moment is quite effective in reducing set recovery, but this ESO resin was also effective. There's a few things that we can change, but I really do think this can be a good option in the future. And so InnoRenew is investing in this. So we really believe that it's a valuable process and a valuable technology. So we are investing in a much larger press. So this is a rendering, but the press should be here no later than August. And so we are doing larger panels, so 1.5 meters by 0.8 meters in width. These are, the fully densified panel. And then we are also having this press capable of expanding. So we have some other I'd say 80% positive funding in the future coming that we can expand the surface area that we can press, not for densified wood because it requires pretty harsh and intense conditions, but for like a larger CLT panel or large wall panel for like plywood or OSB or something. So I will end with there today, but I hope I wasn't watching the time. Looks like I'm almost out of time. I rambled, but if we have time for questions, I'd love to have some. So thank you.
Thank you very much, Matthew, Dr. Matthew. And it's really wonderful presentation, and you gave us knowledge about densified wood. It's really interesting. And we have received some questions. Okay, first question from Philip, and he thanked your presentation first. Then he has some questions. First one, do you expect any thermal degradation of cell walls, example hemicelluloses, during the densification process?
I do not expect any degradation. The only time perhaps this would happen is if we are targeting really high heat treatments. So in later studies, I think Mari, so I think she's here also, would know better, but I think we were targeting like 220 degrees. So for us, I don't think there would be a lot of damage in those.
Okay, the second question is, could the epoxidized, I think, ESO also be partially degraded during high temperature of the densification process, hence lowering its effectiveness?
I do not know the answer to this question, but perhaps Dr. Tamiz or Gaia here would be able to answer that question.
Hello, everybody.
Hello.
Thanks for the presentation, Matif. My name is Ali Temiz. Also saying hi to everybody in this meeting. Thanks for the question. This epoxidized soybean oil, we don't think degraded the cell walls or the wood temperature, because we have some scanning electron microscope results that the walls and the lumens, they are not degraded because this is simply oil. Only maybe the degradation could be due to the high temperature densification, but only the oil will be not destroyed. We have no evidence for that one.
Yeah, I guess in the kitchen you're using oil at high temperatures as well. Yeah.
Yes.
Yeah.
Okay, thank you. Thank you, Dr. Ali, and thank you, Matt. And I have, thank you, Philip. I hope you got your answer. And one final question to Dr. Matthew. It's about when you use impregnated resins and for the intensification process, this wood, when we used for a long period of time, is that will emit any kind of volatile organic compounds, and how did you control this?
So if you are effectively curing your PF resin, it should not be emitting any volatile compounds. If you are under curing, so similar to like plywood panels, if the immediate time after pressing is perhaps the most dangerous time, but the amount of the PF resin formulation is made for the European market, which allows very little free formaldehyde. So this is controlled in this way. Yeah.
Okay, that's great.
But otherwise, it's basically an inert polymeric matrix. Yeah.
Okay, so since you are
Hi, Sudha. This is Samir from Technological University, Dublin. Hi, Matthew. How are you?
Nice to see you. Yeah.
Yeah, just two quick questions that I want to ask here. So regarding the epoxy soya protein treatment that you used for the densification, so did you also do any mechanical testing just to find out how the behavior of the material is?
They have, the student did do that. I just didn't include it in this, but I can hook you up with him and he can share that with you.
Yeah, that will be great because it's quite important to know the structure, the mechanical properties, tension, compression, and the shear strength of this new material. And it's a great work that you are doing there. And the other question that I have, it's in relation to the densification of the structural timber boards. Usually when we are doing the experiments on the laboratory level, we always use the clear specimens, without any knots and nodes. Okay, so I was involved in a project, and the thing is we finished the project. It was adhesive-free timber buildings, and we always used clear specimens for the densification. Do you think we can use the structural size boards for the densification process?
Yes, we do not use clear samples by design. We decided we want this to be a more realistic approach, so we can compress with knots also. Yeah.
Okay, that's very good. Yeah. So do you have any publications on this? On the larger structural size panel densification.
Structural size, you mean
boards? Yeah.
Let's see. I think the largest were 50 probably in width.
Okay.
We make bigger ones though.
Okay.
But for test purposes, they're relatively narrow for little beams, Okay. But I can send you some info on larger samples that we've made. It really comes down to the capacity of the press if you're doing bigger areas.
Exactly. Exactly. Yeah. Anyways, thank you very much.
Yep.
Okay, thank you. Dr. Matt, you received one more question from Hossein. Mm-hmm. Is there a leaching possibility of the oil from the treated wood during the service?
So that's the goal of this epoxidation and curing. So the one step I didn't go into was it's with if I remember correctly, acetic acid. After you are impregnating the oil, this is polymerizing the material. So like the PF, it is fixed in form to avoid this leaching that is common in vegetable oils. Yeah.
Okay, that's great. Yeah. Thank you, Hossein. Thank you, Matt. Okay, I think we are at the end of the session. Thank you, Dr. Matthew, for the very good presentation and answering all our doubts and questions. And
Thanks,
thank you all. Thank you. And thank you all the participants. And the upcoming webinar of this PACK-NIN series is on 29th July. It's about lignin for supercapacitor applications. So who are all interested, please connect with us. So I will send you the message email regarding the next webinar. So hope to see you all again in upcoming webinar series. Thank you all. Thank you. Bye.
Thank you.